Well, some people may think that water quality simulations is as easy as a crockpot recipe. After all, what do you need? A really good hydrologic model, right? Like a piece of roast, and then you add your nitrogen, phosphorus, your veggies, potatoes, let it sit for a while, and that's done, right? Well, maybe. Regulations are often complex. I mean, just look at that. That's a lot of text to read. Normal water quality monitoring programs don't collect data that are needed to do these assessments. We are fortunate at the State Water Survey to have an excellent monitoring program that's headed by Jim Slavikowski, where we often work together to design monitoring programs that give us the data that we need to make the assessments, the programs that is feasible and cost effective. Failure to sample throughout the storm event can result in a large error in your load calculations. You can imagine how expensive that would be if we were to sample every single storm in that way. Cost-effective way would focus on the largest storms during the year. Another issue to consider is how well the river is mixed. Depth and width integrated samples gives you one sample that is actually representative of the whole cross-sections. But you can imagine it takes time. In other situations, when you have rapidly changing conditions, as in this case, when we were evaluating impact of CSO discharges, we only have a couple hours to get there and to sample frequently. So the same technique is not going to work. Other constituents show very strong seasonal effects. Not only you see changes from month to month, you see changes from year to year. In this case, they even alternate. Do I hear corn and soybean rotation? Anybody? In engineering world, design storms rule. Combined sewer overflows for storms of a certain return period. That does not mean that the same return period flow is in the river itself. And by no means it means that a certain probability is there for water quality constituents. So we either simulate the worst case scenario and end up overestimating the impact, or simulate number of combinations, as in this case. Then we add more regulations on top of that. The total ammonia nitrogen, very complex. You have standards that are calculated based on pH and temperature for a site-specific condition at the time of sampling. You have different averaging periods, different seasons, and when you add those two different regulations together, you really get conflicting directions that we need to bring together for interpretation. At the end, we just create even more complex charts and methods that nobody understands, only we do, and we just keep talking about them and trying to explain, and it doesn't work, and it doesn't work. And this is a probability-based assessment. Sewer separation is a popular and very expensive way to eliminate CSOs. The measurements show us that it is effective in improving water quality in some cases. In other cases, it is not. First flush is another concept that's often applied to CSOs. Again, we see that in some cases, some constituents, they exhibit first flush effect. In other cases, they don't. A model is a simplified version of reality. Obviously, the more complex models require more complex inputs and data. Do you want your salsa with tomatoes and jalapenos, or do you want to add other ingredients? Your assumptions in the modeling really affect the accuracy of the results. We can pretend that our simulation results, the easy line, it's the answer that we are looking for, or we can admit that we don't always know all the data. The models that are used to evaluate an impact of some action in the watershed often reflect the assumptions that you incorporate in the model more than the conditions in the watershed. Did we have enough data? So at the end, yes, we can create these pretty maps and show the hot spots, show the clean-cut numbers, but what really matters is the understanding of assumptions, advantages, limitations, and using the right tools that we can solve the puzzle of improving water quality and integrity of our rivers. Thank you.